Welcome to the video for the 15th and 16th question on the example exam. In this one, we'll talk about the location of shear centers for simple cross sections, and we'll also talk about the location of the neutral axis for simple cross sections. Next, we're asked about a cross section and where the shear center is. Remember that the definition of the shear center is the point where any angle at which we apply a force and it goes through, it doesn't induce any moment. Now, for a shape such as this, the shear flow is going to look like this. With all of the member forces going through this point in the middle, right here. Which means that if we apply another force, a shear force, an external force, like at any angle through here, all of our forces go through that point still. That means they can't cause a moment because none of them can cause a lever arm about each other. So that's how that is, how we know about that. And that holds for any cross-sectional shape where that's true. We could have an angle. If we have an angle, it doesn't have to be an equal leg angle. But the point where they meet, where the legs meet, doesn't matter how we apply our load or which direction we show the shear flow going. Shear flow goes through this point, shear flow goes through this point. Some load, it does not matter. It all goes through that one point. Can't cause a moment without a lever arm. Some of you might have been remembering when we talked about this for channels. Thought that maybe it was point A. Because when we did channels, we found that this was something like this. These two flanges are going to cause a moment about each other. And so, as a result of that, we need to apply our shear at some eccentricity from this one in order for it to cause a force coupled with this and the shear that we applied to counteract the moment caused by these. But in a case such as these, there is no eccentricity required. And in fact, that would cause us to have some moment and some bending would result from that, from not having it go through those points. Okay. Once we have solved this, we're also asked what the location of the neutral axis is. So for that, we're given that it is 8 inches wide and 10 inches tall. Let's go ahead and break this into two rectangles. Cool. And it's 1/2 inch wide. So let's just break that into two pieces, and we've got the area, and so the area and we've got y. So I'm going to do, the way I'm going to do this one, is I'm going to look at this whole rectangle, and then I'm just going to subtract out this space. That seems like the easiest way to do it to me. So big and then negative is what I'll call the two rectangles. The area of the big full rectangle, well, that's going to be pretty easy, and that's one of the reasons I did it this way. That's going to be 8 inches times 10 inches. That's going to give us 80 inches squared. The negative space is going to be a little bit less easy. It's going to be 8 inches times 7.5 inches for this and this. And that's going to end up being negative, let's not forget that, 71.25 square inches. The sum of these two is going to be 8.75 square inches. Now, the distance to the centroid of the whole thing, again, pretty easy. For the larger one, it's going to be 5. That's half of 10. And then for these, it's going to be 1/2 of 1/2 of 9.5, which is going to be 4.75. This is in inches. Summing them all together, we're going to get 400, nice and easy. This one is going to be negative 338.4375. Sum them together and we're getting 61.5625. This is AY, and it is, of course, inches cubed. And we can remember that y is equal to the summation of AY bar over the summation of the area. In this case, it's going to be 61.5625 cubic inches divided by our area, which is 8.75 square inches, and that gives us 7.04 inches. And that's up from here. So our neutral axis is going to be at 7 inches up from there. Passes the smell test to me. Okay. Next, we'll be looking at shear flow in this section.